negative, sometimes positive. And so first thing that you do is you take your cosine function and you square it. So now my graph will look like this. Find the average of that, and then take the square root. So it's the square root of the average of cosine squared, or sine squared, whichever one you're doing. Yeah, with calculus, it's relatively simple derivation.
How do you do an average of the numbers if it's just maximums? And they should all be the same. Or are you doing like the whole
curve.
The whole curve.
The whole curve, yeah. So this is known as, well, look what I've done here. I have the square root of the mean of a square. This is the root mean square, which you have seen the RMS value. This is the RMS value for something, and it turns out that this is going to be the square root of 2 times that is going to be the peak value divided by the square root of 2. So what the digital multimeter tells us is the RMS value. So this is going to be equal to epsilon sub naught over the square root of 2. And therefore epsilon sub naught is, so be kind enough.
You said it tells us the EMS value?
RMS,
RMS.
root mean squared.
$167.58.
You know when I ask you to find the RMSE, I ask you to write down the RMSE, that's a root mean squared error. Basically, you take the average value, you look at the difference between it and every other value. But if it's really the average value, if you average just the errors, you'd end up with 0. So you do a root mean square in order to avoid that problem of distressing. All right, so I now know epsilon sub naught. Hopefully I'll remember that. So my formula for the voltage is 160.
167.58.
167.58 volts times the cosine of 370 radians per second times time plus 5. Now, usually in textbook problems, phi is equal to 0, but
Is phi the angle?
phase shift. It's called the phase shift. It's, if you imagine the phaser zipping around like this, when you start the stopwatch, it's an indication of where the phaser is when you start, when time is equal to 0.
So whenever, because we're finding instantaneous at 0, or it's whatever time we want it to be.
Well, wait, ask that again?
Because we're doing an instantaneous problem, we chose the time, so phi is, for this problem, 0.
No, phi is not 0. If at time is equal to 0, if this were the maximum value, then phi would be 0.
Okay.
So let's actually come up with a number, and perhaps that will give you a better picture of it. Is there a question or comment back there?
Well, you said this is defined phi, but we don't have that little epsilon either.
Well, little epsilon at time is equal to 0 equals 100 volts. So I have 100 equals 167.58 cosine 370 t plus 5.
Is t to 0?
Oh, that is 0, thank you.
And so 100 over 167.58 equals the cosine of phi, and so phi is the arc cosine of 100 over 167.58.
And phi should be the same even when we're not at time is equal to 0.
Right, yeah, phi is set by the time you start the stopwatch or the clock, and it becomes set for, unless you disrupt the program or disrupt the circuit.
What's that before the cosine?
You're looking for the arc cosine, just, it's the Hewlett-Packard shorthand notation. And the answer is or actually, one of the answers is
Is this in radians or hertz?
thank you for asking, radians. Is anyone working on this right now? So that we're just gonna stare like a Sergio Leone Western.
You want it in radians, right?
Yes.
0.9314.
Okay.
I agree.
Now, it's radians, you can write radians or not. It's a unitless unit. So what we now have is the equation of epsilon of the voltage coming out of the power supply. Well, we can replace that now. Plus 0.9314. We knew the voltage across the power supply. This is an RC circuit. Okay. Now let's come up with some capacitances.
No.
Oh, are we still done for that?
Well, then we accomplished that part of it. We're not done with the problem.
So the 0.9314. I don't know if we're at the stage, but could you just add like, I guess it'd be pi and a half or pi divided by 2, and like move 90 degrees to get another answer? Because you said there were multiple answers.
Oh,
Like moving quadrants.
we have the cosine is equal to some positive value, which means it's either a first or fourth quadrant
Mhm.
answer. So if you put a negative there, given what I've told you, that would also be equally as valid. I was picturing first quadrant, so I'm gonna put the first quadrant in there. On a test, if I gave you the little information that I gave you here, then there'd be 2 correct answers. Which is a lot of fun grading, because now I have to have 2 separate solutions. But some people help me out by starting on one solution and then jumping over to the other one. Sarcasm, in case you didn't quite catch that. Don't do that.
Wait, so there's two different approaches based on which one you're doing?
Yeah, and you're here, the phaser is first quadrant or it's fourth quadrant. Both of them have the positive cosine value.
And then the negative comes in. Where?
When I put down my phaser being plus 0.9314, based on what I gave you in the problem, is based upon this, the answer actually could have been negative 0.9314. Didn't have to be
I see.
positive.
Then where can you go wrong in doing that?
There's nothing wrong with doing negative. The problem is that you start out with a negative phaser there, and then at some point it suddenly becomes a positive phaser. That's the part where the problem was.
Yes.
That was why it was sarcasm.
Got it.
Some say teachers shouldn't use sarcasm in front of students. That's the old way of thinking.
Would it be a Dr. Fox class?
All right. Let's do a couple more numbers. We got that one. Let's see. So I gave you this. We calculated that. US power supply. So that gave us the magnitude right there. Gave you that. So we found the phase. Resistance. Why don't we make this 60 ohm resistor and make the capacitance. Want to make it 3 millifarads.
With
Yeah, we'll go with that. I might change that number.
alternating currents, is the resistors usually higher, like the resistance number? Because we've been doing it like with 5, 6, and 7.
Oh,
Is it usually just higher? Or you just chose 6?
if you want a nice balance between the resistance and the capacitive reactance, then typically,
Higher.
yeah. In the lab, you'll be dealing with resistances, I think you'll be dealing with 1,000 ohms. And if I made the resistance small, then the capacitor, just so that there's some sort of balance there, would be even smaller, and at some point you'd run into issues, so can we create a capacitor that small? All right. So let's figure out what we do know, capacitive reactance. We can figure out it's 1 over omega C. And omega is 370 radians per second times my capacitance, which is 0.003 farads.
.9009.
0.9009. Anyone else got that? Yeah. All right. I don't like that number. Point 9009. So let's make this.
So .9009 009
Okay. I want it to be. .30 microfarads then. So 3 times 10 to the negative 5th. That gives me 90.1.
Yes.
Okay. Units?
Ohms.
Yep. Now, if you went straight from here, it'd be seconds per farad, but as everyone knows, a second per farad is just an ohm.
It took me only two ohm farads to figure that out.
In another meter at a time.
I feel like that should be like the bonus question on every one of your like very final tests for like for the future. How many units of time can you figure? And then that's like
There's a lot.
You
every
can have to
5
narrow it down, because then people would be gear response days, and, you know, yada, yada, yada.
Well, I mean, in
Well,
physics terms, obviously.
Using only SI units. Anyway. So we know what the capacitive reactance is. The impedance we can now find. The impedance is equal to the square root of 90.1 squared plus 60 squared.
So, when you have a square root or squared number inside of the square root, you just get rid of it, right?
If there were only just a squared number in the middle, but if you got a plus sign, no, that doesn't work that way. answer is
108.249, or 108.25.
units. All right, so what has this told us? Well, I know that my maximum voltage, well, I know that epsilon sub naught is equal to I from the power supply, Z. I know this is 167.58 volts is equal to the power current coming out of the power supply, or the amplitude of the current out of the power supply times 108.25 ohms. And therefore, what is the maximum current coming out of the power supply?
.548 amperes.
1.548 amperes. Well, I now know the three equations for my currents. Because the three equations for my currents, so I is equal to 1.548 amperes times the cosine of no. Feeling that rush for time. Times 370 radians per second. Time plus the phase shift for the current. Remember, the phase shift we found before was the phase shift for epsilon sub naught here. These, we don't know yet. We need to somehow figure out what that angle is. What is that angle? At least we can set it up. So if I call this angle here phi 1, let's stick with theta. Theta. I have a right triangle here. I know that the tangent of theta is the opposite over the adjacent.
I think I fell on the floor, but I don't see it.
I know that the tangent of theta is the opposite over the adjacent. Well, the opposite is VC and the adjacent is VR. I know VC is equal to the current times X sub C, and the resistance is the current times R. So this ends up being, the currents cancel out because they're the same in this particular case. It's going to be 90.1 divided by 60, which is about 1.5. So I know that the phase shift for this is 1.5 ahead of whatever it is for epsilon sub naught. And so this phase shift is going to be the 0.9, written down somewhere. 0.9314 plus 1.5, so this becomes 2.4314.
So it's at that point, 9314 times 1.5.
Plus 1.5 plus. And then the phase shift for my voltage, the capacitive voltage phasor, is this minus pi over 2. Because it lags by 90 degrees. We'll just jump to the phase shift for the capacitance is going to be that 2.4314 minus pi over 2. Whatever that is.
You said, oh, that is 0.8606.
8606.
Yeah.
Now, we have a quick check here to see if this makes any sense at all. I know that the epsilon sub naught phasor has to be between VR and VC, because when I added them together, it has to be between it. My phase shift for here was 2.4 something. My phase shifter here was 0.93 something. The phase shifter here is 0.8, whatever that is, 86 something. This phase shift is between those two.
Indeed so.
So in the lab, it won't tell you the phasor. What it's gonna do is it's going to, you'll have an RC circuit. First you'll do an R circuit, then a C circuit, then an RC circuit. You're gonna have your plot here, and you're gonna have, well, I'll come later. And then you'll have another one, because of course they do different colors. But that is, you know, kind of something like that, and then there'll be a third one that's a different color. And you'll find the equation, do a curve fit for all of them, and this works out rather well.
Cool.
It is.
The application for this kind of stuff in real life is just for the fun of it.
Yeah, obviously, that's the whole point of doing physics.
Something like.
It's all about current control. And, well, it depends on what you're gonna do in life, whether you're gonna use it or not. That was a very vague, generalized answer, and I'm gonna leave it at that. Have a nice weekend.